Hi everyone and welcome to CPS Lunchtime Talk. Nice to see so many of you. I think it fits in quite well with time zones and people not having Zoom fatigue after work, so nice to see a big turnout. Today we welcome Professor Charlotte Williams, who is a Professor of Catalysis and Polymer Chemistry at Oxford. Prior to this, she worked at Imperial for nearly 10 years, where she also did her PhD research, working with Ben and Gibson and Nick Long. And she was previously a postdoc researcher at Cambridge University and the University of Minnesota. Her talk tonight focuses on catalytic activation of renewable resources. So I'll hand over to you, Charlotte. Thanks.
Thank you so much, Tamara, for the efficient introduction, but also thank you to everybody on the committee for this invite. It's truly an honor to be here, invited by your student Chemical and Physical Society. And I'm now going to check that the screen sharing works. But Chiara, if I may ask you to just be my eyes on that and check that everything goes okay. So I wanted to talk to you about some research we've been doing on catalysis, activating renewable resources. And I want to give you two case studies, as it were, one of the catalysis side of my research group and the other about the materials that we make, which are plastics, elastomers, and adhesives. I know that this question of plastics is one that interests many students. And so I also wanted to draw your attention to a report that I co-authored with scientists from Germany and China and Japan. So the chemical societies of the four countries met in 2019, and we had a forum to discuss what science was needed to make plastics more sustainable. And we produced a white paper in 2020, and so that can be downloaded from the Royal Society of Chemistry's website if this is indeed a topic that's interesting to you. So let's think about using renewable resources to make polymers. Of course, most of our polymers, most plastics are made from oil, and that's fine. But in the end, we're not going to need to extract so much oil because most transportation is going to electrify over the coming decades. And so the question is, are there other ways that we can make polymers? And if we use other raw materials than oil, they're going to tend to be more oxygenated. And maybe this can be advantageous in terms of the properties that we get in our polymer. Maybe there are good reasons why oxygens are useful in the backbone. And one of those reasons might be because often oxygenated polymers like esters and carbonates, they have chemistries that are closer to equilibrium. So what we mean by that is that the backbone is more easily and completely broken, for example, by reaction with water, by hydrolysis processes. And this might be useful because there can be none of us on the call today who are unaware of the problem of hydrocarbon pollution from plastics and the fact that they pervade for many hundreds of years and are giving rise to fragmentation and microparticles in the natural world. So the hypothesis here is if we use these natural feedstocks, we're A, diversifying so that we're not solely dependent on the petrochemical industry, and we're B, making polymer backbone chemistries that might be more susceptible to breaking. And of course, some of those might break biologically to give you biodegradation, but others might break down to monomers under controlled conditions, what we might call closed loop recycling or chemical recycling. Now, much of that chemistry still needs to be proven out because, as I said, the bulk of the polymer industry has for many decades been focused on making hydrocarbons, things like polythene and polypropylene, polystyrene. And although polyesters definitely exist and they're an important subsector of the plastics market, they're not used in all applications, and they don't have properties suitable for every application. So what we want to do in this talk is introduce some of the challenges if we wanted to do this, if we wanted to use more oxygenates, both of meeting property profiles for the resulting polymers, but also how would we make them if we're going to completely turn around this chemistry. Now, I trained more than 2 decades ago now in polythene production, ethylene polymerization, and the chemistry that you'd need to do that type of polymerization catalysis is obviously all about forming carbon-carbon bonds, then it's classical organometallic chemistry. If we now want to make some carbon-oxygen bonds into our backbone, we need different types of organometallic chemistry, and that chemistry is very much less developed. So there's tremendous challenges and I would say opportunities here for researchers and for young scientists such as yourselves to address problems in catalysis. So it might be, how do you get these raw materials transformed into suitable monomers? And those raw materials might include plant-based co-products and wastes. They might include carbon dioxide. I'll give you an example of that. They might include other wastes that come out of industrial processes. There are obviously challenges in catalysis around how you get the polymerizations to work efficiently, and I'll talk about that because that's the topic of my research, and also to optimize the properties of those materials. There are also opportunities for catalysis both in recycling and taking polymers back to monomer, or ensuring they are easily mechanically recycled, and in biodegradation, particularly in enzymatic catalysis. So here on the slide, I give you some examples of polymers that could meet this demand to be sourced from renewables. And you'll see that many of them are esters. And we have different sources of raw material to make them, carbohydrates being particularly interesting. And let's move on now and think about specifically why using these bio-based and carbon dioxides as raw materials might have some benefit in terms of global carbon cycles. So back in 2019, I worked on an evaluation of the technical and economic potential for using carbon dioxide at scale. And this was a piece of work with quite a few scientists worldwide, but also with economists and political scientists. And the outcome of that is clearly we have enormous amounts of carbon cycling on Earth. And this slide is showing you what emits CO2 and how it gets what the sinks are globally. And so you can see that the classic, energy, heating, cooling, heavy industry, steel, chemicals, cement, transportation, agriculture are the really big emitters of CO2. And the sinks are, of course, either land-based through photosynthesis or they're into oceans predominantly. And the numbers are absolutely staggering, aren't they? We're talking about gigatons of these. And in order that we have habitable planet, we've got to get this back in balance. And it's not the case that any one of these arrows can be alone the solution to the problem. We have to have multiple actions to get net zero. And one of the things that may be interesting in this context is thinking about how our chemical industry can achieve this, because we are a significant emitter. And we're also an emitter that it will be more difficult to decarbonize because it isn't only about heating and cooling or a particular form of energy vector. There are sort of multiple emissions pathways from the chemical industry. And if we do that, then thinking about using carbon dioxide has benefit. And we can think about different ways that you might capture carbon other than through those natural processes in the biosphere or the lithosphere. You might choose to directly air capture it and concentrate it and then transform it directly into some kind of product or store it underground. And very likely we'll have to do plenty of this in the coming decades. We may also think about options to capture carbon dioxide through the plants that grow and then use those as raw materials or co-products to make useful chemicals. And if we do that, we have another opportunity to capture carbon and put it into our materials. But it's a very different process to how we make nearly everything today, because that relies on oil that was, stuck into the ground many thousands of years ago. So as part of this piece of work, and I refer you to the paper if you want to read in more detail about this, we examined different opportunities for using CO2, and we looked at the break-even cost per ton of CO2 used. And so you can see that those with the wide bars are going to be using quite a lot more carbon dioxide up in terms of tons. And those with narrow bars aren't using very much. And then those that are above the line, they need subsidies to work as carbon dioxide utilization technologies. So cement, BECCS is a bio-powered carbon capture and storage, so where you burn biomass and then pump carbon dioxide underground, and these other options, methane and DME and Fischer-Tropsch and so on, they don't economically work at the minute, so they need subsidy in order that those markets could compete with the current ways that you would make predominantly fuel-based products. On the other hand, those that are below the line, below zero, they already have profitability, and they can already use carbon dioxide to make their products, and so they include lots of natural processes, forestry and trapping of CO2 into aggregate and so on, biochar, a way of making carbon from biomass. But they also include, interestingly, things like methanol and urea from carbon dioxide. And you see the one that is a very narrow bar with the red arrow, but has a very high potential to deliver economic return. And that's making a particular type of polymer called a polyol. And the first part of my lecture is going to focus on this. So the key take-homes from this slide are that all of these technologies where we use carbon dioxide need further investment and development. The second one is that polyols have high technological potential, so they're further along the pathway to being realized, and they could potentially be quite a profitable way to use CO2, but they don't use massive volumes. They use small volumes, but they could have a role as a front runner technology in pulling behind other CO2 utilizations. So now let's think about these CO2 polyols, which are shown on the right-hand diagram. And what we mean here is where we take carbon dioxide and epoxide and a catalyst, and we make a polycarbonate. So the carbon dioxide ended up in the backbone of that polymer, and so did the epoxide after it got ring opened. And that polycarbonate is low molecular weight typically and has hydroxyl end groups, and that's why it's called this polyol, because it's got hydroxyl end groups, and those then can react on with a diisocyanate and give you a polyurethane in one manifestation of a common use of the polyols. There are other uses from EU. So this is the market opportunity that you saw on the prior slide. And some of the advantages of it, it's already proven to work well with waste CO2. And it's also a technology that can be retrofit into existing manufacturing plants. So you've got the potential to bring this technology to market faster because you can use it in plant that's already built. Life cycle analysis already shows that you get significant reductions in greenhouse gas emissions by making your polyol this way compared to the conventional way. And the properties of the material you make are suitable for use in a number of different areas, including as foams or in coating, adhesive, sealant, plastic. These arrows show some things that need optimization in this field. Still, there are questions of process efficiency, and of course, catalysis falls in there. The products still need demonstrating in a range of other sectors, and this really needs to still be taken to very large scale. So there are some industrial case studies here, but it needs to still keep translating in order that this really changes the way that these materials are made. On the left-hand side is a polymer that has the alternative way that CO2 might be used, and that's through intermediary trapping of the carbon dioxide through photosynthesis into sugars in plants. And then those are fermented to give you a lactide at the top of the slide, and that can be polymerized to give a plastic. And this polylactide is a leading bio-based plastic. It's one of the larger volumes, about 1 to 2 million tons of this plastic are made every year worldwide, and it's biodegradable. And it certainly has lower greenhouse gas emissions than incumbent plastics like polystyrene or polypropylene, and has some applications in packaging, but there are still some things that need solving about polylactide chemistry. For a start, it uses grown crops. It needs an agricultural industry to feed it. And in future, we would like to use wastes and wider types of different biomass for the raw material. There are some recycling questions about PLA, and in principle, it's highly recyclable because it's an ester and they're relatively straightforward bonds to break, as we've just said. But in practice, that technology is not yet implemented at scale. There are issues still with its properties, and there are some related to that, still some challenges to solve in processing it as a polymer. So let's move on to the polyols, because that's really the topic, not the PLA. I don't want to devote too much time. So here you see some images of the foams that you can make from carbon dioxide polyols shown in the top left. and also a result of the life cycle analysis showing you greenhouse gas emissions and fossil resource reductions. And it's worth saying that that life cycle analysis conducted in Aachen by Gertler and Leitner and so on, and Bardo, of course, that was conducted on a polymer that didn't have very much CO2 in its backbone. It only had about 10% CO2. For various reasons, the catalysis that German group were using doesn't take much CO2 up. You will see later on in the talk that we can really improve upon that 10% and have up to 50% of the backbone of the polymer from CO2. In the center of the slide, you see some work that we did on using captured gas. And I'm not going to run through all the impurities in the gas, but the short message from that is that we took some CO2 from a coal-fired power station. It went through purification before we used it. But when we did use it, we saw that the catalysis functions really well, even with the captured gas and with some of those impurities present. A number of years ago, I founded a company, Iconic Technologies, that's based up in the northwest of the UK, just outside of Manchester. And so the other two pictures you see, which are a bit more of plant, and they are pictures from Iconic of their demonstrator plant, which makes 20 kilos of this polymer a day. And that's in Runcorn. It's on an ICI side just outside of Liverpool. So let's move on and think about the chemistry and the catalysis to make these polymers. So these polymers with carbon dioxide in, they work in a alternating copolymerization, and you need a catalyst for that to work. And the catalyst has two different types of intermediates in the cycle. One is an alkoxide, and then when carbon dioxide inserts into that alkoxide, you form a carbonate. And that carbonate then attacks an epoxide and regenerates the alkoxide. So in our slide at the bottom, we're going from the green species in the middle over to the right-hand side and back again. And it's long been my group's hypothesis that two metals are needed for this catalysis, particularly if the metals are light or first-row transition metals. You need two so that you can access that transition state and have enough low barrier to have reverse side attack by the metal carbonate onto the epoxy. It's also worth saying that exactly the same mechanism works if instead of carbon dioxide, you have a cyclic anhydride. And I'm not going to belabor the point, but on the left-hand side of this sort of mechanistic sketch, you can also make polyesters by using anhydride epoxide alternating copolymerization. So my group have worked in this area for a number of years, and we've been particularly interested in bimetallics, as I said. And we started out looking at two zincs in a particular macrocyclic ligand framework, which you can see here. And they had quite low activity, turning over about 20 turnovers an hour. But they were unusual because they worked at 1 bar pressure of CO2, so they could really turn over under very accessible conditions, low CO2 overpressure. And then later we began to look at other metals, and then later still in 2015, we became interested in mixing two different metals, and we saw something quite interesting, which was that when you put zinc and magnesium in this scaffold, you see an enhancement of activity that's really significant compared to either of the homodinuclear. So zinc magnesium as a complex is much more active than zinc zinc or magnesium magnesium. And then from about 2018, we began exploring other metals. And today I'm going to talk to you about cobalt and magnesium together in this macrocycle scaffold and what we've learned. So it's worth saying something about the catalytic mechanism, which we've been studying now for about 10 years. And of course, a mechanism only exists as long as the kinetics substantiate it. And so what we really do when we make these measurements is make lots of kinetic measurements to determine rate laws. And our rate laws have shown us that this polymerization proceeds with a fast carbon dioxide insertion and a rate determining step that involves metal carbonate attack on coordinated epoxide. One of the reasons we began looking at heterodinuclear catalysts was that this mechanism that we'd studied for homodinuclears really was pointing us towards different roles for the two metals. Now I'm going to leave it at that for now and show you about making cobalt magnesium or zinc magnesium catalysts. And the important point here is that it took us a number of years to deduce this, but actually the heterodinuclear catalysts or metal complexes are actually the thermodynamically more stable product compared to the homodinuclears in most cases. Of course, this is not always true, but certainly in the cases that I'm going to show you today, it is so. And so this means we have two different synthetic routes. We can start from our free macrocycle, which, by the way, is really quite easy to make. And many generations of students, including undergraduates, have made this in my lab. It's a high yielding, straightforward synthesis. So we take that macrocycle, we metallate it with diethyl zinc, and then we can add in a second equivalent of metal to get to the heterodinuclear species. And we do so free from contamination by the homodinuclear because that heterodinuclear species is thermodynamically more stable. And in order to prove that, we can also establish that by taking zinc and magnesium and heating them together over a prolonged period of time. And then what happens is that we have exchange of the metals, as I say, hot and over a prolonged period of time. And then we end up with ever increasing quantities of the heterodinuclear species. So I hope this establishes for you that you can feel that they are stable, these catalysts, with respect to decomposition to the homodinuclear pairs. So here we are making now a magnesium cobalt catalyst. And this was a decision that came out of lots of years of careful kinetic measurement and also understanding of the best metals for each role in catalysis. Here is some characterization data on this catalyst because it's not so straightforward as magnesium zinc compound to characterize, because cobalt 2, as you all know, is a D7 electron configuration, and so is paramagnetic. And because of this, we've made use of two perhaps a bit more unusual techniques, one of which is XPS. And we did these studies with an academic at UCL, Anna Ragutz. And Anna, her work was very useful to help us establish that we hadn't had any oxidation of the cobalt. So you can see that the cobalt binding energies are very consistent with cobalt 2, both for this heterodinuclear catalyst and for the homodinuclear analog that we always make so that we can really understand activity increments. And then the other thing we did was looked at cyclic voltammograms of all of our compounds, magnesium, cobalt, and magnesium cobalt. And we plotted the cyclic voltammetry data in a slightly unusual way because we plotted, if you like, distributions for that electrode potential. But what you can see is that the ligand has an oxidation up at about 0.4 volts versus ferrocene. And cobalt compound shows two oxidations, as you would expect, because there's two cobalts there and both of them can be oxidized to cobalt 3. Whereas our mixed metal species shows just the one, and it's at a different redox potential. And that is providing us with further good evidence that we don't have significant contamination from any homodinuclear species. There were other proofs that we used. I'm not going to go through them. They were to do with magnetism. But the important question is whether this mixed metal species is more active in catalysis. And the short answer to that is that it definitely is. So if you look at the turnover frequency data for polymerizations run at 1 bar pressure of carbon dioxide, you can see that it's showing about 1,000 turnovers, 1,200 turnovers an hour, whereas the cobalt is 700 and the magnesium is about 370. Now, those data are all conducted under the same conditions, and so we can be sure that this is a proper comparison of activity. And we're really seeing a much higher activity for the mixed metal species than we might expect. The other point to note is that we're making polyols. So you see the GPC trace in black. We have a low molecular weight, which is exactly what you want for this type of product, and a very narrow dispersity of molecular weight, a Gaussian distribution. And that is, as I say, important when we use those polyols to make further products. So now what I'm going to do is to compare for you some of this activity data under a few different conditions. I don't want to bombard you with too many tables, but in the top is the data you've already seen. In blue is data that's collected at higher pressure. And what's happening in these higher pressure runs is you see quite a big leap in activity. The bottom one is at higher temperature. So it's at 20 degrees higher than the one above it. And of course, we get a higher rate with higher temperature. But why do we get this enhancement when we run under higher pressure? And this is actually an important question, because it isn't that the catalyst has a pressure dependence in its rate law. It's rather relating to the ability to efficiently stir the polymerizations. And when we're able to do so, we get out of diffusion controlled regimes. And in the pressurized reactors, we have very, very good impellers, stainless steel impellers that really improve that mixing of reagent. Now we can see underneath the two blue entries, magnesium and cobalt under the same conditions with the good stirring. And again, we have some activity jump for them, but still, once we're into these regimes where there is no viscosity limitation, you can see that really this heterodinuclear catalyst, the magnesium cobalt one, it always outperforms either the magnesium or the cobalt under any of the conditions. It also outperforms mixtures of the two, which just give the law of averages, the rule of mixtures value. And that's because although over time, cobalt and magnesium would redistribute to give the heterodinuclear compound, they don't do so on the timescale of these experiments. And way back at the bottom is what happens with zinc, and you can see where we began and how far we've come, as it were, over a quite significant period of time as well, but research takes time. Now here I'm just giving you relative rates, so you can see now with the better catalysts we're about 1,000-fold more active than we were with zinc. So this probably doesn't mean too much to you as numbers unless you understand how the rest of the field is performing. And so here I've given you some good other catalysts that are out there in the field, and you can see that really this is the fastest catalyst at 1 bar. It's very selective, it gives you good control of molar mass, and it makes the right type of product with the hydroxyl end groups. I don't want to go through all the examples, but you can see there that most of them are giving turnovers around 100, and then a very active one with zinc there is about 400, but it's not very selective. It has quite a big selectivity at 1 bar. And we can also see that we hit selectivity problems with temperature at 1 bar. And so black trace tells us about making polymer. Blue trace tells us about making cyclic carbonate, which is another possible byproduct. Everything's good until we get to 100 degrees, and then polymer productivity at 1 bar drops right back down again, and we start making a lot of the wrong product, this cyclic byproduct. And the reason for this is probably to do with CO2 availability, which will drop as the temperature rises by Henry's law. The solubility will fall with temperature. And so we can overcome this by running at 20 bars so that the reaction has sufficient CO2 to be able to turn over. And then when we do so, the activity increases up to that value we'd seen before of about 24,000 turnovers per hour. And so now when we're running at 20 bar, and we've really got this catalyst under the absolute best conditions it can be under, then we can compare it against some other good catalysts that are out there. And we can see that it's really got a very competitive rate with many of them, much better than the cobalt salens that are out there and some of the dizincs. Now there is one that's got a higher number there, 77,000. This is a sort of one result. The majority of results for that dizinc are considerably lower, around 1,000 to 4,000. And so I think that this is probably a very exceptional performance for that one, and that maybe the more common experience with those beta diaminates is that they're quite a bit lower. In any case, we have very good selectivity, high carbon dioxide uptake, and we make polyols regardless of pressure. Of course, this doesn't change. So now we've done some kinetic analysis here, rate law determination, so order in monomer, first order, monomer, there you go, first order in monomer from our semi-logarithmic plots, first order in catalyst using these methods of Jordi-Perez, 0 order in carbon dioxide pressure over 10 to 40 bars, so really no increase in activity provided you have the sufficient CO2 with temperature relationship managed, and you have good stirring, which all of these polymerizations would have. So we can get to a rate law, and we see that it's once again a rate law probably in which carbonate attack is going to be rate limiting. So here we come back to our catalytic cycles, and we can say that provided that we have sufficient CO2 and we have temperature control, so that CO2 is dissolved, then we expect that CO2 insertion is fast and epoxide insertion is rate limiting. We have to manage this backbiting reaction, and that's important too. And the other point to make is that as we polymerize, this chain moves. So if you look at the formal site at which the anion is bound, on the left-hand side, the anionic portion is bound to cobalt in the carbonate form. But on the right-hand side, when we've transitioned into the alkoxide intermediate, it's now formally coordinated at magnesium. And so this is something we've called chain shuttling, but we also believe is a very critical feature of why these catalysts perform well. In essence, they are set up in their coordination geometry to accelerate this chain movement. The acetate ligand that is also coordinated by this catalyst, shown on the opposite face to the polymer chain, is important and plays a role in facilitating chain shuttling. There is no oxidation of the cobalt during the catalysis, so cobalt-3 is not present. Here you see an X-ray structure that kind of confirms the idea that magnesium might be the site at which epoxide is coordinated. This X-ray structure is not of cobalt magnesium, but is of a zinc magnesium complex. And you see that the epoxide mimic, in this case THF, is coordinated at magnesium, not at zinc. So that would be perhaps consistent with its higher oxophilicity. And that would give us the notion that it would be the other metal, zinc or cobalt, that provides the nucleophile, the carbonate, to do this attack step, the rate limiting step. So the next thing we did was to do an I-ring analysis. So here you're looking at the temperature dependence of the rate constant, and you're using that to extract the transition state Gibbs free energy. And we can see that for our series of catalysts, there are differences between them. They're quite small, but the error bars in these numbers are very low. And so they are real, and exactly as you'd expect, a magnesium cobalt compound has the lowest transition state energy, whereas the magnesium compound, which is the slowest catalyst, has the highest one over a range of different temperatures. And from that, we can deduce the transition state enthalpy and entropy. And shown in solid squares are the enthalpy values, and shown with open circles are the entropy values. And what we see here is that the lowest enthalpy is with cobalt-cobalt as a catalyst, and the highest enthalpy is with magnesium-magnesium as a catalyst. Now, of course, you will be aware that the enthalpy has units of kilojoules per mole, whereas entropy is just joules per Kelvin per mole. So the bigger determinant will be the enthalpy, but the entropic factor is important. And we see that the entropic barrier is the exact reverse compared to the enthalpic one. So for the open circles, the lowest barrier is now with magnesium-magnesium, and the highest is with cobalt-cobalt. And so if we look at our catalyst that's showing synergy, that's showing better performance than either of its contributing partners, we see that it is, if you like, the best of both worlds, because it combines the low enthalpy in the transition state that cobalt appears to deliver with the low entropy for the transition state that magnesium appears to deliver. And this is a really quite interesting finding, because although synergy is very commonly claimed in catalysis, it's very rarely rationalized. And we appear to have a rationale that relies on a particular metal delivering a particular function in the transition state. So as I've said, magnesium reduces the entropy and plays the role of coordinating the epoxide. So perhaps it pre-orders the transition state. Cobalt reduces the enthalpy, which is completely consistent with it providing the carbonate nucleophile that attacks the epoxide. And as I've said, this is our hypothesis that explains how synergy functions in these types of catalysts. Now, there is a question about the extent to which those findings would be more generally applicable, and that's something that we continue to probe, both in this field and in others. But in the remaining few minutes of my talk, I want to tell you about something else you can do with these catalysts that take up carbon dioxide. That's something really surprising and really quite cool. But you can take these same types of catalysts and you can mix in up to 4 different types of monomers in your reaction, and you can get out very specific and single sequences in those polymers. You can either make block polymers or multi-block polymers, and I'll give you a few examples of how that works, but I realize time is tight. So this is a way that we can sequence block polymers using a single catalyst, a mixture of monomers, and exploiting the fact that all of these polymerizations are very controlled. And how this works is that we essentially have a common intermediate to 3 catalytic cycles, and we dictate which cycle we're in by controlling the chemistry of the metal intermediate. And so here you can see that the common intermediate is a zinc alkoxide. It could be indeed any metal alkoxide, but let's take zinc. And by controlling whether we have a carboxylate, a carbonate, or an alkoxide formed, we control which cycle we're in. And we have discovered that from mixtures of monomers of these types, anhydrides tend to have both the lowest barrier to insertion in the transition state, but they also form the most stable linkage. So now I'm looking over at the right-hand side where you see the barrier height in those very rough sketches trying to show you how you go from an alkoxide to a range of insertion products, and the stability of the linkage formed. We also see that carbon dioxide has quite a low barrier, but it forms a much less stable linkage, and so there's some possibility for reversibility in CO2 insertion chemistry. In contrast, caprolactone, lactones tend to have higher barriers and the least stable linkages of all. And so through understanding this chemistry, its kinetic but also thermodynamic origins, we can really control the block sequence in the polymers that we made. And although this seems very obvious, it actually had not been just sort of noted at all prior to 2014 when we began the work. And even in the time since then, it's now become apparent that it's routinely correct. So this works not just for zinc alkoxides and the types of catalysts I make, but it works for all sorts of different catalysts that people are using, including various organocatalysts and organic molecules, other metals. This is really quite a generally applicable finding. And what's more unusual is to find catalysts that don't obey these rules. So we've been exploiting this to make all sorts of block polymers. And I'll just, as I say, give you a couple of examples. So here's one where we take propylene oxide, lactide, and anhydride. And we took those monomers deliberately because they are already commercial products made at quite large scale. And they are bio-based in the case of lactide, or could be in the case of the other two, if society chose to make its chemicals that way. And we began by studying these insertions just from mixtures, and we exposed it, in this case, to an aluminium catalyst. And you can see when we look at the consumption, we can see that the first thing that happens is the anhydride is consumed, and then after about 8 hours, the lactide begins to be consumed. We can also show that when we have the right catalyst, even though we're making a block polyester, and I'm using green to show you the PLA and blue-pink to show you the alternating polymer you make from epoxide anhydride. So even though we're making a complete polyester backbone, there's no transesterification. So when we look at the molecular weight and dispersity profile of our polymer long after reaction is complete, over more than 8 half-lives of reaction, we don't have any change in dispersity. There's no transesterification. And so this was work of an undergraduate student, Dan Mulryan, who later on went to Imperial to do his PhD. But Dan was doing his final year project and did the work on the previous slide. But he also discovered that because this is a living polymerization, we can do some nice tricks by adding in more monomer mixture many, many times. He did it up to 7 times. And then he made a 27 block polymer. It has the same information code, if you like. It's always ABA, but it repeats many, many, many times. And here is some data to support that finding, because you can see the GPC traces are continually evolving to higher molecular weight as Dan adds progressively more monomer mixture into his catalyst staying alive throughout the reaction, and a molecular weight of the polymer increasing linearly with the number of blocks added, and the dispersity staying really narrow, so fully consistent with high polymerization control. And of course, that 27 block has got a very complicated Greek name that Dan went and looked up, but that doesn't matter. The point is that you can get this exquisite control of sequence from just 3 monomers and controlling your catalyst properly and understanding, first of all, the kinetics and the thermodynamics, and then exploiting it to your end. So why do you care? Why does that matter? It matters because the sequencing in polymers absolutely affects their macroscopic properties. So although it may seem a sort of abstract thing down at the molecular scale, it of course has a fantastic effect on what you can use that polymer for, how it responds mechanically, how it responds thermally. And block polymers are very well known to phase separate into different regimes on the nanometer scale or the tens of nanometer scale. And those phase separations are very important in dictating properties also. So what we're thinking about in the first part of the lecture is all on the molecular scale, right? Is all on that atomic scale, if you like, but putting in of different molecules in particular patterns, the classical sort of chemist way of thinking about it. But what we need to think about in the next few slides as we address properties is how chains interact with one another, how they form different phase-separated structures through aggregation of different chains into domains, and then how that affects properties. So, okay, here's another switch. This time we're using CO2, and we're making blocks where we have the rigid block at the chain end and a flexible aliphatic polyester in the middle, shown in green, and we've got carbon dioxide in that in the blue-red portion, just through the typical polymerization we opened with. Everything works in the same ways by the switch catalysis here. And here I'm showing you that the polymers we make are optically transparent, so exactly as you would want for any kind of application. And we're going to think about applications either as a thermoplastic, so a ductile plastic, or we're going to think about them as pressure-sensitive adhesives. Actually, we're not going to do the adhesion because I took it out, but we're going to think about them as plastics. So here we're making those polyesters using our switch catalysis. Here's some data looking at conversion time and some proofs that we've truly made the block polymer. There were many more in the paper, but I'll just give you a couple of them here. We typically make 8 proofs of block polymer formation. And here showing you that because this chemistry is really controlled by the composition of the mixture you start from, it's really easy to change how much of the green block versus the blue-red block you have. And we have been able to vary that so that we hit compositions, for example, where we have about 25% of the blue-red block, and that would be typical of a thermoplastic elastomer. So that we would call a hard block, and we have, for a classic thermoplastic elastomer, somewhere between 20 and 30 weight percent, usually, empirically. We've also been able to hit compositions where we have a 50-50 mixture of them, and that's the one I'm going to talk to you about today. And we have studied its phase-separated nanostructure, and it is in the regime of thermal and phase-separated properties where we'd expect it to be a plastic. So here you can see some DSC data showing you that the blocks are phase-separated. So you have 2 glass transition temperatures, one around -50 for the green portion of the polymer, one up about 110 for the rigid polycarbonate portion. Here, some thermogravimetric data showing you that the decompositions are typically beginning above 270 to 80. So it's got reasonable thermal stability, and it's got a reasonable processing temperature window. And that would typically be the temperature above the upper glass at 110 and prior to it decomposing. But that's very important if you make a new polymer, because you've got to be able to process these materials hot through extrusion or casting processes. So here, as I say, we have a polymer that's got 15 weight percent CO2 in it, and it's 65 weight percent bio-based because of the green block, which comes from Castellan. Here's some DMA, where we're looking at storage and loss moduli for these polymers, and again, confirming the operating temperature window up to about 100, and then a processing temperature window from 100 up to about 250. Here, a bit more on the way it degrades. But here, perhaps the more important set of data from your point of view, what does this mean for the properties of the material I'm making? Here we cast these typical dog bones of our polymer, and we put them on a tensile testing rig, which is essentially exerting a force on that dog bone and stretching it. And you can then plot the stress against the amount that the material stretches, the change in length of that material. And we can see that it's a typical plastic in that it has a yield point around 7 megapascals, and then it eventually breaks about 20 megapascals, showing 1000% elongation compared to its original length. So it's got a moderate tensile strength, as I say, about 20 megapascals, certainly well within the regime of something like polythene, has high ductility and extensibility, higher than many plastics we use today, and it has good tensile toughness. So this is important because it's not brittle, and that's really a problem with a lot of the current bio-based materials, is that they would have tensile toughness is way down in the 1 to 2. And actually there's the tensile toughness for commercial polycarbonate from bisphenol A, and you can see that that's a horribly brittle material as well. And as a consequence of which, you need to use processing aids, you need to use plasticizers to be able to apply those materials. Here, just a couple of Ashby plots where I would compare the UT, the ultimate tensile strength, against elongation at break. And you can see that we've really hit a nice regime for our new 50-50 composition polymer. It's much tougher than PLA, which has already been toughened, or than bisphenol A polycarbonate or various other polycarbonates, much tougher than the polycarbonate on its own without the green block, so showing you the benefit of having that present. And again, plotting toughness against stress at break, we can see that it's got a moderate strength, certainly within the range of usable materials, but a really high toughness. So there is definitely more to be done here, but I hope it gives you an idea of the promise of being able to control which catalytic cycle you're sitting in. The final point, which we opened with, was that ester chemistry and carbonate chemistry is closer to equilibrium. And here is a demonstration of that point, because if we just put the polymer into water, nothing happens over many days, over 290 days, everything is fine. And the same in weak acid or weak base. So that's important because our polymer needs to be able to be used. And we can't have something that hydrolyzes in a toughened plastic application just on a droplet of water. That's not okay. But what we can do is when we've finished with using that plastic, we can control its degradation. In this case, we're using a little bit esoteric conditions in a lab, but we're using a pH 3 from this PTSA, toluene sulfonic acid, and we're doing the reaction in toluene with a bit of heating. But once we do that, then within a few days, 5 days, we've completely broken down the polymer. And of course, if we wanted that to happen within hours, we would simply conduct it hotter as a reaction, and that would be very feasible. And we've broken down the polymer to remake pro-monomers. We haven't exactly made the same monomers we started from, but they could be reused in polymer synthesis. So this topic of making and breaking is one that we're very interested in my group, and we continue to explore. This definitely brings me to time. And so what I hope I've shown you is the potential for using carbon dioxide and bio-derived monomers, and the importance of controlling precision in structures, and control polymerization catalysis as a route to do that. I haven't talked to you at all about how any of this last chemistry I've shown you might translate to scale. I mean, for example, there are still problems of cost and efficiency of extraction from bio-based, and integration with waste systems, and polymer property improvements, and degradation kinetics and biodegradations. All of the things in red we are trying to address in the group through various activities, through catalysis, through process optimization, through degradation studies, and continual work on what are the properties we get and how do we feed that back into the structure of what we're making. I want to really thank the people whose work featured in the lecture today, and they're shown in the names. The red names are the researchers who were working currently in the group, and the blue ones are people that have moved on, showing you where they went to after they finished. And of course, Anna Ragut is a colleague of yours at UCL. I want to acknowledge the economists who've been very important in proving out the benefit of using carbon dioxide in these types of applications, and also various funders here on the slide. So thank you very much for your attention, and I now will attempt to stop sharing so that I can come back and hand over to Chiara.
Thank you so much. That was such an interesting talk. I can't believe that such seemingly simple chemistry could be the solution to our current climate troubles. We can now open for any questions that the audience has. If you want to raise your hand and unmute yourself or type it into the chat, let me know. Adam, do you have a question?
Hi, Charlotte. You kind of scooped me with my question at the very end, sort of by saying about the biosourcing of all your materials. I was wondering what explicitly you'd done for the, if you'd looked too much at the green sources for the epoxide source things. That was like the one missing part of the equation, and you've got these three components: CO2, a plant-based source. I know there are green epoxides out there. I was wondering if you'd incorporate them and what you'd worked on.
It's a great question, Adam. Thank you so much for asking it. And it's, of course, very important. Right, we can answer this. So my group did do some work on green sourcing of cyclohexene oxide. Actually, we did that while we were at Imperial, and we were working with a team of Germans who were looking at the cross-metatheses of plant oils. And so when you cross-metathesize a triglyceride, which you often do actually to make either fuel or to make other monomer precursors, you often make cyclohexadiene as a byproduct. And we looked at oxidation of that more than a decade ago. And so that potentially could be a bio-based route. It was still in academic labs. It would need a process chemist, optimized, but it's feasible, that oxidation, certainly. So that would give you cyclohexene oxide at scale if you so desired it, but it would be dependent on triglycerides, and they are not the cheapest things. There is another possibility to get to that kind of ring system from lemon peel, and we've looked quite a bit at that to make limonene oxide. It works well. The monomer is more problematic in the catalysis, and so there's plenty of challenges that we're still trying to crack there in incorporating it into materials. That's very possible. But again, we're stuck in a waste peel scenario, and whilst there is actually quite a bit of point source of waste peel in juicing companies and so on, it's not that big a composition of peel. So still you might have some cost implications there. So if you really want a cheap epoxide that could be bio-based, the right one would be probably ethylene oxide or propene oxide. Croda have a commercial process to make ethylene oxide from bio-based sources, I guess from ethylene through ethanol routes, but I don't know too much. So that certainly could be possible. And these catalysts work with ethylene oxide. We don't do it because ethylene oxide is a very dangerous monomer. So people in my lab don't do that. That's feasible. Propene oxide you would make from propene, and there are bio-based routes to that also that are going through scale. So long answer, but the short answer to it is yes, it's possible, and it's a great question. We need to do more of it.
That's a good answer. If I can sort of leave him with a very quick, hopefully, follow-up. On the mechanical side, obviously I've got interest in tough materials. Have you looked at incorporating cellulose nanocrystals and trying to make a nanocomposite out of them, sort of have a green nanofiller side of things?
That's a great question. I would love to revisit this chemistry. No, I haven't done this with these types of polymers. And yeah, I think this would be a great idea. We should talk, Adam, actually, about this offline. We did some work many years ago with cellulose nanocrystals into PLA, and that's definitely an effective and well-known strategy now, and many others worldwide are working on that more than we are, but that's a great idea. So you get a green each way, right? Green filler and green resin. Yeah, we should definitely talk. This would be a great plan.
Cool. Yeah, I'll leave it. Draw your name out afterwards. Cool. Thank you, Kiara, and thank you, Charlotte.
Thanks. We have a question from Susan as a last one, whether the heterodinuclear catalyst, could the metals interchange position within that, and would you know?
Oh, this is such a good question too. Would we know? Well, I mean, that would all be about the relative rates at which the metals could be exchanging, right? And the timescales of the detection methods. So I would say that within the detection methods that we have used, and we've addressed a range of timescales, including those using optical spectroscopy that would be some of the shorter, we don't see any evidence for that. But I think it's impossible to rule it out absolutely, because if the timescale for the exchange were we're shorter, I don't think we would see the average, but I think there must be some possibility for them to exchange in order that you can make the heterodinuclear through mixing the two homodinuclear compounds. But I cannot say for sure the extent to which that might be happening on the timescale of these polymerizations. But I can say that we don't see any evidence for the homodinuclear compounds in the polymerization, either optically or through a range of different spectroscopic techniques. But it's a really good question.
Thanks so much. In the interest of time, you did say you had to go sharply at 2 o'clock. So I just want to thank you again so much for your talk. The Society is very grateful to have you.
Oh, it's my pleasure. Thank you so much to the audience for tuning in and wishing you well. Hoping to see you in UCL one of these days. Cheers.
Yeah, definitely. Thanks so much.
Bye-bye.
Bye.